So far, we've looked at atoms, we've looked at the periodic table, we've learnt that there are many different types of atoms and that they all have different masses and stuff and structures. But what we haven't looked at is how they hang out in reality. Because the truth is that most atoms don't like to actually hang out on their own. They don't want to be lonely. And it's because they need stability from each other. On their own, most of them are very unstable. So let's take a look why. Here is the periodic table. And it looks a little different than what you've seen so far because it's color-coded to show the different groups or types of elements that we now know exist. Essentially, we can break most elements into two groups. Metals, that's these ones here in blue, and non-metals, the ones over here in red and the hydrogen over there. And just where they meet, you actually have a whole heap of what we call metalloids. They're elements that share properties of metals and non-metals, so they're part and parcel. The metals over here, they're quite strong, they're very shiny, they're malleable, which means they bend, they don't break. They're very good conductors of electricity and heat. Non-metals are pretty much the opposite. They are dull, they are brittle, they're not as strong as metals, and they don't conduct heat and electricity very well, so they're good insulators. These metalloids here are actually in-betweeners. They have some properties of each. Now the big thing to remember here is that the structure of the atoms that we have determines whether an atom is a metal or a non-metal. You'll learn more about that in years to come, but its structure is what determines its function. And the biggest point we're going to make here is that its structure determines whether or not it likes to group together with other atoms or not, because there is only one group of atoms on the periodic table that actually want to be on their own. And that is this group here. These are the noble gases. And noble gases are the only atoms on the periodic table that actually like to exist just on their own and not joined to any other atoms at all. That's because their structure makes them very stable. Everyone else is slightly unstable, and to be stable they actually have to join up with other atoms, which we're about to see right now. So this is what noble gases look like on their own, atoms not joined to anything, and we call that monoatomic, which means one atom on its own. Now because all of these atoms you can see here are all the same type of atom, this is actually what we call a pure element, or all atoms of the same type all on their own. Now let's look at everything else. Most atoms like to group together for stability, but you have to think of it in two ways. You have to think about who do they want to group with, and you've got to think how do they like to arrange themselves. And I'll explain that in a little bit more detail. Who they want to group with. Do they want to actually group with the same type of atom, or do they like to group with different types of atoms? The next thing you have to think about is how they like to arrange themselves. Do they like to group together in small groups or in large lattices? Small groups we call molecules. The big lattices are what we call crystals, and we're going to have a look at that now. Who do they like to group with? If they like to get together with atoms of the same type, then we call it an element. So here we've got sulfur. It's actually a group of 8 different sulfur atoms all joined together. And here we've got graphite, which is the lead that you find in your lead pencils, which is lots and lots of carbon atoms joined together. If you find them grouped with different types of atoms, we call it a compound. So this is carbon dioxide. This is carbon and 2 oxygens joined together. This here is a picture of table salt, sodium chloride. These are the sodium and then the chlorine atoms all grouped together in this arrangement here. So that's who they want to group with. Now let's talk about how do they arrange themselves. If they like to group together in small distinct groups like this, We call these molecules. If they rearrange themselves in repeating patterns that just keep going on and on and on until you run out of atoms, we call them a lattice. So essentially we know them as crystals. So sodium chloride table salt we know as a crystal. It's lots and lots of sodium and chlorine atoms, one sodium for every chlorine, arranged in this lattice format to form a crystal. So when we name these, we actually name them based on who they're grouped with and how they've arranged themselves. And last but not least, I've just added this in on the end because this is to show you carbon, and it's the main atom that we're all made of. We're carbon-based life forms, and it's a unique atom. Okay, it's actually very stable, and it joins together in many, many different ways in nature, and since mankind came along, in many unique unnatural ways too. This here is diamond, where carbon actually gets together in a 3D format with bonds all different directions into this really tight, strong structure. And as we know, diamond is the strongest structure. But if you rearrange the bonds to be like this, you get graphite, which is in your lead pencils. So it's nowhere near as strong as this, but it's actually made of exactly the same type of atom. It's just how they are arranged that makes them stronger or not. These guys here are what we call buckyballs. They are man-made carbon balls. And this here is a nanotube. And we're developing these to actually apply them with what we call nanotechnology, making atomic-sized machines to do work for us.